everyone to today's edition of Water Data Forum. Water Data Forum is a web series presented in partnership with Cleveland Water Alliance, Midwest Big Data Hub, and WEF, the Water Environment Federation. Today's topic is Catching the Unseen, AI's role in tackling microplastic pollution. We'll have plenty of time at the end for Q&A, but if you want to ask questions while you think of them, go ahead and use the Q&A function at the bottom. Sometimes our panelists can get to them before the end as well, but we will definitely have time at the end for questions. We always have a really interactive group here, so we look forward to welcoming them. So let me introduce our moderator for today's session. This is Alexander Tompkins, CEO of Remedion. And Alexander, go ahead and introduce our panelists for today.
Thank you, John McMullen, Samantha Martin, Cleveland Water Alliance, Midwest Big Data Innovation Hub, and WEF's Intelligent Water Technology Committee for hosting this webinar. We have an incredible panel of experts with us today to discuss the crucial topics of microplastic pollution and how artificial intelligence can assist us in tackling these pervasive pollutants. Let's meet our panelists for today's discussion. Dr. Jan Ilwager is an associate professor in the Department of Civil and Environmental Engineering at Wayne State University. Her research focuses on water treatment and water quality. Her group's microplastic research includes understanding the fate and transportation of microplastics in natural and engineered water systems, developing high-throughput microplastic sensing technologies, developing data tools to identify sources and pathways of waste plastics entering the environment, and conducting community outreach campaigns to reduce plastic pollution. Rachel Miller is the founder of Rosalia Project for a Clean Ocean, co-inventor of the Coraball, CEO of Coraball, a National Geographic Fellow, and Explorers Club Fellow. Rachel is focused on protecting the ocean by specifically addressing the problems of marine debris and microplastic pollution through cleanup, prevention-based education, embracing innovation and technology, as well as conducting solutions-based research in urban and coastal waters from surface to seafloor. Dr. Andreas Prada is an accomplished civil engineer with extensive experience in data analytics and environmental research. Currently, he applies his expertise at Frost Defense Envirotech Inc., developing predictive tools and machine learning models to optimize agricultural products application, significantly reducing uncertainty and enhancing effectiveness. Additionally, as an assistant research scientist at the Prairie Research Institute, Dr. Prada leads pioneering initiatives in PFAS and microplastic mitigation. And as you know, I'm Alexander Tompkins, CEO of Remedion, a clean tech company dedicated to providing pollutant-free alternative food and water products. We utilize proprietary systems to remove physical contaminants like microplastics and chemical contaminants like PFAS from water in order to produce our pollutant-free consumables. Currently, Remedion is in the process of launching our microplastic-free bottled water line and are working with a Warwick, Rhode Island nonprofit to construct a pollutant-free community garden. The first question for our panelists will detail a broad understanding of microplastic pollution. Who is responsible, where these contaminants are found, when do we become aware of them, how does microplastic pollution affect us, and why is this a major problem? Let's begin by hearing from Rachel Zoe Miller. Rachel, what is microplastic pollution?
Thank you. Microplastic pollution, we'll just get straight into it, of course, is definition-wise, when bits of plastic, they can be made that small, which we call primary, or they can have broken off of something bigger, which they call secondary, 5 millimeters or less, which is actually a really big range because 5 mil you can see, it's like half the width of your pinky nail, and you get down into where we spend a lot of our time, which is working on microfiber, a subset of microplastic, and that you need some kind of magnification to see. And then nanoplastics are another category below that. So broadly speaking, microplastics are pieces of plastic and synthetic material that is less than 5 millimeters, but can take on different shapes and forms, including fibers, fragments, films, beads like little spheres, and the like.
Thank you for your insights. If I'm correct, you just got back from the Arctic Circle, and that would be a great time to talk about where these contaminants are found.
Yes, we've had some amazing research expeditions over the last year that included up as far as 81 degrees north in the Arctic and also in the Southern Ocean and around the Antarctic Peninsula and South Georgia. And the best way to say it is that microplastics are not found in every single sample people take, but they are found in every region people look. And so we can say with confidence that they are ubiquitous. Our work, we are looking for microplastics and anthropogenic or man-made microfiber in the air, sort of in suspension. We're using an air pump, and in the surface water, although we have also sampled the entire Hudson River, looking down in the water column as well. But this primary work that we've been doing from pole to pole has been surface water and air atmospheric suspension. And again, we're finding microplastic, mostly microfiber for this work that we're doing. Our collection methods are to do what's called a grab sample and then filter. So other people do things like trawls, where you tend to get the bigger pieces of microplastic. Again, it's a big range. We sort of need more words for this. And but doing the grab sampling with the filtering lets us catch the smaller pieces. And yeah, I can say with some confidence, it's ubiquitous, air and water and soil.
Thank you for your outstanding response. Dr. Prada, do you have any insights?
Yeah, that was a very good response by Rachel. I would add or let's say she has been sampling in the Arctic, but most of my work has been on cities. So in the case of a city, we believe that the life of a plastic doesn't end in a landfill, because we have detected microplastics in landfill leachates that are sent to wastewater treatment plants, but wastewater treatment plants are not designed to treat microplastics. So microplastics end up going back to the environment by the wastewater treatment, but the wastewater effluent and biosolids. So that's how we can find them in rivers and then in agricultural soils.
Thank you. And Dr. Wagger, how does microplastic pollution affect us, and why is this a major problem?
All right. Hey, I think microplastic can affect us in many ways. I mean, they can go into our water, surface water. They can go to our water supply, and when they go to our water supply, they can go to our drinking water. So also when they are microplastic in the aquatic environment, and those organisms that living in the water, they could accumulate those microplastic in those organisms, and then so basically there could be a build up in the food web, and then we human being consume those food, we could also consume those microplastic in our body. So basically, we human being, we could consume the microplastic from water supply, from food we eat. There's already a number of research and report, including our research from our group, that we found that microplastic did exist in drinking water supply, in food, in fish. So it's definitely that we are taking microplastic into our body. So speaking to what exact impact that if we take in microplastic into our body, right, what impact that could cause. There are research out there. So we actually, our group did some research, use zebrafish as a model to expose zebrafish to nanoplastics. And then we did find that those zebrafish that exposed to those nanoplastics develop some adverse, like the behavior and hypertension, inflammation, and also genetics disorder from the zebrafish. There's many other research that found like animals that exposed to the microplastics have similar adverse impact. In terms of the human response, so it's a much broad topic. So, but and not many research out there yet in terms of exact human health impact. But there are a few papers come out indicate that the microplastic may be associated with some lung disease, asthma, because a researcher did find microplastic in lung tissue, blood tissue. So I'm saying that we still have a lot of work to do to find exactly what microplastic can cause to human health and ecological health, but there's definitely evidence that show that it does cause some impact on ecological and human health.
Your answer was, oh,
Can I add something?
please.
I'm gonna put the link in there. Yeah, that was great. Oops, whoops, no, I'm putting it in here. Just a month ago, just over a month, 5 weeks ago, there's a paper that came out in the New England Journal of Medicine. I'm sure you guys maybe have seen it. It's pretty fascinating. I just put the link in there. It's open access, but it's very cleverly done. It's obviously hard to test how this affects humans because we can't dose humans. Like that would be terrible. And so, there has to be creative ways to understand just correlation. So this was a very creative study where they took arterial plaque that was removed from, it was like 200 people who went in for that kind of surgery. So the stuff was taken out in order, so these are people who were sick. Arterial plaque was then looked at. 60% of the people had microplastic in their plaque. And then the study looked at long term, and the people that had microplastic had a 4.5 times higher likelihood to experience stroke, a heart attack, or die within 34 months of the surgery. And it's a pretty fascinating, again, it's not a causation situation. It is a potential link, but one that has gone farther than a lot of other studies have gone. And I think people looking into this will find it interesting to add to the pile of growing information about the human health implications.
Thank you
That's
so
great, Rachel. Yeah, that's great that you share the article. Yeah, I have a few articles I can share later. So all those articles did find some correlation about microplastic and human health. That's awesome.
Thank you both. Your answers were both engaging and informative. Let's move on to question 2. Our next question for our panelists involves the use of raw data for a realized impact. We'll start question 2 by hearing from Dr. Wagger. Dr. Wagger, how does the study of microplastic pollution leverage data for impact?
So that's a very big question. So I probably will to talk about some research that work that our group is doing. I'm pretty sure other panelists will provide some inside information from their experience. So our research group are doing a lot of research to how to identify where those microplastics come from, and then how to reduce the pollution from sources. The reason that we focus on this area is because we know that microplastic is very small, right? Once they are into the environment, it's very hard to clean them up. I mean, we could pick up some debris, large debris, like big bottles, plastic bottle. But when we talk about those small particles in milliliter, micrometer, even nanometer, it's really hard to remove that. So our research group focuses on how to identify where those microplastics come from, and then how to identify those, and then to reduce the sources. So we are collecting data from all sorts of environment, from wastewater, from drinking water, from soil, like green infrastructure soil, urban soil, from surface water, and also from sediment, to look at what kind of microplastic are there. And then we integrate those data, so basically what microplastic are there, and also together with what they look like, particularly for those larger pieces of plastics, what their texture looks like, and what the color looks like, and also where we collect it, what's the landscape associated with those areas we collected. So with all those information we put in a library, we already have built a microplastic data library. So that library is in alpha version testing right now. So that including over 2,000 of the samples, including, as always, including all those microplastic and large plastic samples, debris from the environment, also the environment, as well as post-consumer plastic product. So with those data together, we also developed the CNN. It is a machine learning algorithm. So with those algorithms, we can track, or also tell us, all right, what kind of these plastic pieces could come from what kind of a plastic product. And then that information will give us, particular community of scientists, to say what is top contribution for those microplastic in certain environment for the particular region there. So that's what we have been doing. Right now we are expanding our work. So we just got a grant. Like it's a new grant just came in. So we're going to expanding our work with communities, with probably 20s of communities. We start with 4 or 5 community, and then we are expanding our sample collection to 200 community in the Great Lakes area. And then with those community enjoying our data collection, and we'll use those data, as I said, it's metadata. So we're going to use a picture, image, the data collection, sample information, and also we use Raman spectrum. So the Raman spectrum will tell us whether it's plastic or it's other material or other synthetic material or it's non-synthetic material. So with all those data collected together, we're going to refine our tool to track where those pollution sources come from in a particular community, particular region. So that can inform those leaders in those communities to take action to reduce those pollutions.
Your passion on the subject matter is evident. Thank you for such an outstanding response. Should we hear from Dr. Prada now?
Sure. So data is the basis for all the studies right now. So the ones that Rachel had shared, so are based on data collected, all the studies. And that's the route that any contaminant has to go before we can implement any legislation. So recently we have seen, as an example, what's going on with PFAS, and now after years and years of research, like the US EPA came up with the regulations in drinking water. So microplastic has to go the same route after years of data collection and studies to finally identify what are the implications for human health. So as Rachel was saying, it's very difficult in humans. But one thing that I can add is the influence that microplastics in agricultural soils can have on bacteria. So bacteria attach to anything. So they are in agricultural soils, and there is this new material, the plastic, that contains also chemicals and additives. So bacteria add to the plastics and react to those new chemicals, becoming even resistant to antibiotic treatment. And those bacteria go into the food chain, and then that is the bigger problem of like having antibiotic resistant bacteria. So that's one of the biggest implications that I see with microplastics, besides the direct effect on our bodies, but is the effect on bacteria and how that translates to humans.
Thank you for your contribution. Rachel, can we hear from you now?
Yeah, so I'll balance it with some work that we're doing on the microfiber side in a very specific way. So we figure we do these expeditions and we're filtering water and we're getting some number. It could be depending on how many samples we take, and if we're doing it in the Hudson River or we're doing it in the Southern Ocean, tens, dozens to hundreds to thousands of individual particles. And these individual particles, depending on what process one is using to identify them, could take from 4 to 30 minutes per particle to figure out the source. And we can't stop this if we don't know the sources. We have to know what is there in order to prevent it. And so the opportunity that data science can, or the impact that data science can bring to all this, is making it so we can speed up the identification process. In one of the ways is to speed up the identification process. So if we can just have at the human side or even a machine side, a magnified image of, say, anthropogenic or man-made fiber. And then an algorithm trained, a data set that's been trained, can come in and identify that, the color, the shape, the width, and potentially the material. We can start to zero in on what's really out there. And as far as textiles go and microfiber goes, you know, the way we see it, what this will help us learn is, on the prevention side, is answering the question, are there point sources for this stuff where there's like a factory making something that's purple, and that's why there's a lot of purple delta fibers that are 25 microns wide in a place, and we can track it back? Or is this multiple diffuse sources of all of our collective clothing falling apart when we wash it, when we dry it, when we wear it? And if that's the case, we need our clothing to be more resilient, and we need our clothing perhaps to be made out of something that is bio-derived and bio-benign, at least one of those. And so it's this power of data to make these identifications, to drive understanding, to be able to prevent these problems, significant problems. So that's what we're trying to do. Is we're working with Staffordshire University in the UK on using AI to come up with an app, or to create the app that we can have a global citizen science microplastic mapping and monitoring project. And this is for the smallest of the microplastics and microfibers. We call it CSI for the ocean, and we're sharing, we're taking methods from forensic science as well as marine science to bring it all together. But ultimately, its success will be because of AI.
Thank you. That's just such a great concept and bridges us right into our final question we have for our panelists today. It's on AI advancements and observing pervasive pollutants. Dr. Brada, what does the future of AI detecting microplastics look like to you?
Yeah, so both Professor Wager and Rachel have mentioned how it will help with detection. But I will add that we are creating a giant database. So every week or every month, like a lot of new papers are coming out. So we need the power of computing to help us like summarize and identify those compare between contributions, and find like topics where they overlap, and then demonstrate the same thing, or so we can identify as I said, the health effects on humans, on bacteria, and on the ecosystems. So that's when it comes handy, the artificial intelligence, to help us navigate through those giant databases and have meaningful outcomes.
Thank you, Dr. Prada. I know you touched on it before, Rachel, but I'd love to hear more from you. How will AI help in the future with detecting microplastic pollution?
I think what AI will do is shorten the distance, shorten the time, shorten the amount of people and effort that needs to happen to go from collecting information about this problem to actually doing something about it, in terms of making the actual data drive decision-making. So again, whether that's driving funding that supports research on making alternative materials, or like something that's made out of waste organics, that's happening, but it's happening in small batches. And in order for it to make an impact, it needs to be made in big batches. Also in driving something like our project, obviously, it's easy for me to come back to our project, because what we see is, if we can enlist not just students, but community scientists from all over the world to look and see what's in their air and water. It'll work with atmospheric deposition, just using a bucket, and also a bucket in the water, and filtering, which can be done pretty simply. Again, we can start to understand if there are any point sources, And those are low-hanging fruit for solutions. At least you can talk to one group of people or a smaller group of people, or if this is going to have to be or continue to have to be a textile-wide thing. So I think there's very little that's more valuable in our ability to have an impact than managing the data that's being collected and using AI for good.
Thank you. That's such incredible insight. Our company Remedion will be doing something similar, where we will actually have artificial intelligence control our water quality and when we're going to change our water within our community garden. So a lot of what we've been talking about really revolves around the identification processes of artificial intelligence. Dr. Weyer, do you have any insights to add to this?
I would add, like, I think you all have a great point. I just would like to add a little bit, I think, or summarize a little bit, or you're talking. You guys have a great talk point. I think AI in terms of microplastic impact in the future, I think overall, I think it's make the detection, reduction, all those things is more, how to say, higher efficiency of the says, because we can use AI to grab those data more efficiently, analyze those data more efficiently. Another thing is also accuracy, like higher accuracy to basically to identify those plastic resources more accurately. I'll come back to my research again. It's example, when we develop those C and AI language machine learning algorithm to incorporate our Raman spectrum to identify microplastic from the sample, from the environment samples, right? Our methods can reach to like over 99% of accuracy. As I say, we have over 2,000 data. We train our data and then use 80% of the data training, 20% of the data prediction and validation. And then we compared with our own machine learning tool with a standard library or like the Raman spectrum library to comparison. We did find like our machine learning to have a higher accuracy of this overall 30% to 50% of more accurate. This thing is because microplastic, when they go to environment, they have degradation. After degradation, we all know that after weathering, so make the identifications become more challenging because their characteristics will change. When we use a Raman or other testing tools, so when we compare to the standard spectrum in the standard library, it's going to change, give us uncertain results there. So I have to say efficiency, accuracy, and also definitely last point, it is data-driven decision and actions. That's what we would like to say is because there are so many sources, point sources, non-point sources, and also all those sources depends on the particular, like the specific region. So for example, in some region, they might not have recycle program. That might be there's a lot of plastics come from some debris, and also near highway, maybe the microplastic come from the tiring, from the tire driving. So there's so many different sources there. I think that the AI will really help us for get the data, like data-driven decision actions. I would say geospatial data-driven decision and actions for specific region if they want to take the actions to tackling this problem.
Professor Wager, is your Raman system able to estimate concentrations, or you just detect the type of polymer?
We need, so for the concentration, we need to count them. So we can use ImageJ, we count them. We use
count them.
Yeah, we need a automatic counting. So basically we scan the samples and then automatic counting. So the Raman spectrum, it is just among those particles we found there, and then we will detect them one by one to see whether it's a Raman spectrum. It's identification, so basically.
Mm-hmm.
We used polarizing light microscopy, which is something taken from forensics, to as well particle by particle with one human. And thinking about that as you were talking is that for all of our papers that we've published with these expeditions that we've done, in particular the Hudson River, where we've sampled from the Adirondack Mountains to Ambrose Light, the whole Hudson River. It's interesting because you get agricultural, suburban, extremely urban, industrial, alpine, like all these regions in one relatively small river, 300 miles. Anyway, we have had only one analyst look at every one, which is a big ask of one person to look at 4,000 particles. But it's until we have some machine-based ability, we can't risk that, say, you see blue a different way I see blue. And when an actually important characteristic is color, we have it the same color being seen differently by different people and being called something else. And so, like you said, it's moving towards machines being able to identify the same thing the same way every time, no matter what the circumstances. It's going to be very valuable instead of. So we've dealt with it by asking one person to do an extraordinary amount of work. So at least we know that all of the blues are in the same blue, because that is how she saw that blue. So yeah, I think it'll make a big difference.
Most definitely. Where Remedion will be applying artificial intelligence to our microplastic-free bottled water line is our inline Raman spectroscopy data will be transformed by artificial intelligence to create visual representations of our water quality. That water quality graph will then be posted as a live feed to our website to ensure our customers know the quality of our products. So thank you all for everything. I mean, this has been an incredible panelist we've had today. At this point, do we open it up to Q&As?
Sounds good. We do have one question in the Q&A so far, and I encourage other attendees to drop those in there as well. But we do have a large number of water utility folks typically on this call, and so this question I think is related to that. So Andres, you mentioned EPA regulation around microplastics in drinking water. Can you talk a little bit more about that process, and then water utilities are going to be interested in how they can filter out microplastics, and so any insights that you all have on best practices for that, I think might be appreciated.
Yeah, thank you for the question. Now, what I tried to say was that the EPA released the regulations for PFAS like a few weeks ago, a week ago. So I was comparing like the emerging contaminant of PFAS compared to microplastics. So PFAS has been studied for a longer time, and now it gets to a point that we can take measurements and regulate their use. But microplastics is still under research, and then the effects on human health are not well understood. So we have to get to that point of like detect those problems and say, okay, we need to regulate filtrate microplastics for drinking water facilities, for example. So sorry about the confusion. I just tried to give an example to compare microplastics with another contaminant as PFAS, if that answers the question.
May I add a comment there, Alex? So since I have done a lot of work in drinking water plant, we will sample the we collaborate with water utilities. So we sample drinking water like source water. We sample the water after each treatment process, for example, coagulation, flocculation, sedimentation, and filtration, and treated water. The good news it is from our report, the treated water like a water treatment plant, it's actually very, I would say it's pretty efficient to remove microplastics. At least our data show like over 98% of removal. So I think what we need to do, it is how to punch that a little bit left there. That's basically, there's still, as I said, 98% of over removal. It's a very good removal efficiency, but there's still some there.
Yeah,
So
that's very true. For drinking water facilities, I wouldn't be worried about microplastics. The the problem are there is more exposure with plastic bottle water. So every time that you open your bottle, your plastic bottle, you are adding microplastics. Every time that you leave your bottle under the sun, the plastic is degrading and coming into your water.
that's good
So
point. Yeah.
so tap water can be say it's safe in most part for microplastics, but then again the main problem is with when we put it in plastic containers.
This is where Remedion is truly championing our microplastic-free bottled water line. We will be producing our water, filtrating it, purifying it, and bottling it in glass with cork T-tops in order to ensure that our customers do not receive microplastics in their product. One of the effective wastewater treatment options that we have is our hydroelectric water purification system. It co-generates purified water and hydroelectricity while producing that pollutant-free product for your consumer. We utilize a combination of purification and absorption processes to accomplish this feat. And I also just dropped the link in the chat as well.
Thanks for that. We do have a couple of other questions in the chat. Alexandra, if you can't see those, let me know. But one is sort of about that evolution of regulation in that space, but then as well, how we can rapidly detect microplastics, maybe using some of those machine learning techniques that were talked about before.
This is a tough one, I think, depending on how small you want to see. That there's some organizations that are working on pump-based, FTIR-based detection to do environmental samples, but they're still not quite seeing the sub 100 micron fibers and things like that. So there's a little bit of which, like I said, we need a few more words inside of just microplastics to describe what's really out there. I think there needs to be a couple more categories, but yeah, that's something to work towards for sure. I mean, for us, we foresee right now, we're still going to need humans to do the filtration, and then the innovations, the opportunity for innovation is big to do scanning of filter papers or of slides with this. We use a tape lift with a material called Easy Lift tape. Again, came from forensic science to transfer what's left on the filter paper onto a glass slide so we can use polarizing light microscopes. So for us, we're still needing humans to get 400 times magnification pictures of each of the particulates of interest. And then it would be identifiable, at least as a first immediate step. But my guess is that my fellow panelists are using something more automated. Is that correct?
There are, as I said, Rachel, you got a right point. It really depends on the size. So the size difference from my experience, it really depends on how efficient or how quickly you can analyze a sample. So like micron size, millimeter size. I mean, millimeter size, it's much easier. We can actually see it. And the micron size get a little bit harder, challenging, because we need a microscope or some sort of appliance or to detect it. And also when it's go to nanometer size, it's going to be even more challenging because the nanometer size really small, really tiny, and then whatever analytical tool we use, for example, FTIR, Raman, and then the wavelengths or signal become very weak, and then also there's a non-noise background noise there, so the nanometer size is very become challenging. It really depends on the size. I know there's one company they are doing. They claim that they have a product OPTR. So I'm not endorse the company. Okay, there are some research there, but if you're interested, I can put there. I think it's OPTR. It's you can take a look at that. Yeah, I have not used that machine yet, but I have a click to work that machine. He said it's okay. It can do some automatic scanning and then can go down to nanometer or something like that. So that's something very challenging for nanometers. So again, I come back to the AI. I think we actually have an idea right now to once we get the new project going on, we are actually thinking about it to link the microplastics and the microplastics. So basically to when we have those data, right, we have a lot of data, already published data and other groups data or our own data. When we collect the plastics, right, we have some range in microplastic, larger pieces. We have some in smaller pieces. So there are maybe some correlation there between those micro and the macron. So we have been thinking if we can find some correlation or some sort of underlying mechanism there, in one day, we hope that we can look at those larger particles can give us a lens into those smaller particles. So,
That would be nice.
yeah.
It would simplify things. That's for
yeah.
Yeah, we did a study outside. So within our Hudson River trip, one of the sort of, we just did as much as we could. You know, expeditions are expensive. So we did as much as we could. And we did a wastewater treatment plant study. And we haven't published this yet, but we sampled at the outflow. So we called that 0. That's where the marked on the chart, the effluent coming clean effluent from the wastewater treatment plant. And then we sampled half mile, 1 mile, 1.5, and 2 miles up current and down current of the 0 point at the surface, the mid water column, and 1 meter above the river floor in the Hudson at a rural, suburban, and urban, actually on the East River location. And, you know, sort of very preliminarily, we were finding similar concentrations in the water column with that sort of same thought of like, let's make things easier, that if that holds up, and this is just kind of an initial study, and I don't know if you guys did depths as well, but if you could just take surface samples, at least in rivers similar to the Hudson, I'm sure the hydrodynamics are different everywhere, but that would be nice, because not having to take depth samples would simplify monitoring, you know, because that's where we need to turn. And I think where AI and big data has an opportunity is to simplify the monitoring. So we are still understanding the problem, but we know enough to take some actions, and actions are being taken, from policy to innovation, like what Alexander's doing, to other types of consumer education related actions, like people washing differently or using a core ball or something like that. But the monitoring is going to be really important, and knowing if we find the big stuff, it means there's also little stuff, or if we find microplastic on the surface, it also means it's in the water column, is going to be really helpful.
I would just like to add, I believe the balance between prevention and removal, we do need to emphasize the prevention side of things. I don't know how many of our jeans, t-shirts, sneakers, we're all just wearing plastic products. We're not wearing natural materials that can return back to the environment when they shut off. So I believe that on the regulation side of things for microplastics, prevention is just as important as removal. And I think it's way easier, if not more. Yes, if not more.
Yeah, I agree.
I believe a national shift towards cotton-based clothes would be way more attainable than putting these crazy limits out and expecting people to meet them on a specific timeline.
It's tough though, because the naturally based clothes, you know, that derived from something natural like cotton isn't free of problems. And we are finding huge percentages of the fibers in natural places are anthropogenic cottons. They have dyes. The dyes are not that natural. In fact, they don't even need to tell us what's in them. They're often not something we want to drink, or we don't want creatures drinking them. There's additive things like wrinkle releasers and dye setting agents and things like that. So yeah, even beyond trying to move, like there's lots of ways to affect this. In addition to, I don't know that we can fully vilify synthetic clothing entirely, because it's also unrealistic. We need to stay warm and dry when we do things outside, and temperature regulated and that kind of thing. And so I think, yeah, it's super complex for sure, as far as the clothing side goes, but not insurmountably so. But I think on the clothing side, it really has to be all prevention, pretty much. With the wastewater treatment plants, are doing a great job. Just like we said, 98% is incredible, but it's 98% of a lot. So that means 2% is still a lot. And so prevention ends up, and the way I usually explain it is, this is like pickup on this side, like cleanup is like spilling a big thing of table salt in a field and then trying to go pick up the individual pieces. It's just not efficient or effective, or probably even possible at this point with the technology we've got.
That was an incredible analogy that I will definitely borrow.
It's all yours.
you.
All right, we do have another question in the Q&A that we can throw to the panel. Rachel, you were talking about different types of plastics earlier, and the differences between fibers and others. For example, this questioner is asking about petroleum-based or hydrocarbon-based plastics versus maybe some of the newer ones that are more bioplastic and break down more easily. Are there differences in the ways that you guys approach those? Are there differences in the tools that may be able to be used to detect those?
I love this question, and what you're thinking about here, because we're thinking about this a lot too, is like, is this just about plastic clothing or petro-based clothing? Again, we need more words. Plastic as a word is just too broad for now, all the materials that live under it. Yeah, from our side, I have to say that using the polarizing light microscope helps us differentiate between something that is from a sort of flora or fauna base, like fauna for us would be wool or alpaca, something like that. But we're in our work and with our partners, I'm not aware of automated opportunities there. And I hope that we get to keep working on this, because that means that bio-based or alternative materials are making their way into especially textiles, and being able to understand those is really, really important. I mean, I'm talking about this as a potential solution, but we do need to know more about the implications of that as a solution, and is it better, and that kind of thing. So how about you guys? Young-Lee, have you been working on that, like differentiating?
We have been working on that. We basically use Raman and FTIR to spectrum. So we basically that does give us like the spectrum does give us what kind of particular material, like the specific, for example, PVC, PET, or what nylon, or what other material it is. Sort of for the background, I think there's some project going on out there. But I think the thing is become, it is as Rachel, as you say, there are so many material out there. It's really, we need like some of those more advanced like a data tool to basically to identify all sorts of different material. And I mean hundreds, thousands of material. I mean, if FTIR, Raman, those commonly used tools, they can also use to identify other materials, not just plastics, not just polymers. So it's really, I think, at this point, there's really need a lot of more work to definitely to look at those bioplastic side. We have not get into the bioplastic side yet. So right now we are focused on the petroleum-based plastics, or our algorithm is also developed based on the petroleum-based plastics. But that's great question. That's something we can think of in the future.
Yeah, and part of it's going to be that as some new materials are coming out into the world, that those libraries, the FTIR Spectra library, the even what we know as far as the ranges for polarizing for birefringence and polarizing light microscopy, we need to know what the new stuff is, like what their numbers and what their spectra look like, so that they can be identified as a new thing. So that'll be interesting coordination really between the scientific community and the textile innovation community as well. That'll be important.
Yeah, exactly, Rachel. I think that's a really good point. I think that's the library out there, build a library, keep adding those spectrum or data into the library. That's really important. So as I say, we are going to expand our project to collecting those post-consumer products. So as more of those bio-based plastics goes into product, goes into the market product, we hope to add in those spectrum samples into the library. So I think that would be really useful.
It would be good to ask funders or whoever's doing this to sort of require that work gets done as these new materials get developed. That somehow, I don't know how this gets done on a global way, but
I think NIST, the NIST, National Institution of Standard, NIST, they do have a branch, they do have office programs to collect I think they're focused on FTIR spectrum for thousands of materials. So I think that's, I think also the database is probably open database. I think definitely that's worth to check. NIST.
Cool. And I know that
another very, very important industry is food packaging that needs a lot of innovation, because we cannot keep putting our chips in a bag that lasts for hundreds of years. So we need to change the whole food packaging and create something either reusable or degradable, biodegradable.
Where we come into this is we do not specify on the chemical composition of any contaminants, where we are actually a size class oriented company, where we remove that up to 0.1 nanometer contaminants from the source water to produce our pollutant-free consumables. So I would like to see a real effort on deciding whether or not we need to move towards these bio-based plastics or get rid of plastic entirely. I think petrol-based products in our lives are really starting to damper down on our health.
Great. Well, thank you all for the discussion today. I'm going to invite Samantha Martin from our partners at the Cleveland Water Alliance to come back and talk about an upcoming session for this series.
Thanks, John. Let me go ahead and share this slide here. So thanks again to all of our panelists. Thank you to our moderator, Alexander, for a great discussion. And this webinar is being recorded. It will be emailed to all registrants, even if they weren't able to attend today. And stay tuned for information on our next webinar. The date is still being finalized, but the topic will be cybersecurity in water. So we'll keep everyone posted on when that's scheduled this summer, and we'll send out information to everyone, to all the registrants, and we'll send out the recording as well. Thank you so much, everyone, for participating today. Thank you for the questions.